Hello, welcome to Stochastic Gradient Descent. So here's an introduction to Stochastic Gradient Descent. It helps power deep learning and is an extension of gradient descent. So that's the first thing. A recurring problem in machine learning is that large training sets are necessary for good generalization, but large training sets are also more computationally expensive. SGD reduces computational cost by updating parameters using a single data point or a small mini batch instead of computing gradients over the entire data set. This makes each update much cheaper and allows models to begin improving immediately, enabling efficient training on large data sets that would be impractical for full batch gradient descent. So here's an overview of what I'm going to be talking about. First, I'm going to be talking about the gradient descent equation, the learning rate in the equation, a full gradient descent review, stochastic gradient descent, the mountain analogy to stochastic gradient descent, and SGD implementation, and then comparing gradient descent and SGD, and then showing different SGD algorithms. So let's talk about the gradient descent equation. First, we have the data, right? N samples, x1, x2 to xn. And that's the full sample size, okay? Or the full data set, data population. Then we're gonna try to minimize or optimize a likelihood function, right? With theta being the parameters, okay? And then we're gonna divide that, we're gonna take a summation and then divide it by the total population. And that theta could be representing what we saw earlier, W and B. Okay, so we saw that in the previous video with linear regression where we set parameters W, which is the slope, and B, the bias, which is the intercept. Okay, and we're trying to solve for that to minimize that loss function. So the loss function computed over the full data set for regular gradient descent. Now here's the update equation step by step. We've got theta t plus 1 is equal to theta t minus eta, and then that likelihood function. Theta t is the current model parameters. Theta t plus 1 is the parameters after the update. That's the gradient of the loss with respect to the parameters, the delta L. And then eta is the learning rate or the step size. So that's pretty much the standard gradient descent equation. And we've seen that earlier. Now, I do want to talk about the learning rate, put a little bit more emphasis on it. There's two types of learning rates, right? There's a learning rate which is small, and we could see that it converges slowly but surely to the minimum, right? If you have a smaller one, right? So it basically, it's going to take a little bit of a longer time, but it'll get there. And then we've got a large learning rate, right? Where basically we could get to the minimum pretty quickly. It's a large step size, right? That gets us to the minimum. But the problem with a large learning rate is that it could also overshoot. And this will be a little bit more clear when I talk about the mountain analogy and some give you some more examples. So remember the gradient descent implementation, right? We've got that y hat equals wx plus b, the gradient of the loss with respect to the parameters. We've got the update equations that I just mentioned. This time we're making it more explicit with the w and the b instead of the theta. And here's some pseudocode, right? And we want to basically set a tolerance and then minimize that tolerance so that convergence is achieved, right? We've got the update equation, the loss, and then the gradient. And you can see that after a certain amount of iterations, it converges, okay? Where the loss is minimized, okay? So you see that the loss goes to 0. So let's do a recap. Compute the gradient on the entire data set, right? That's computationally expensive. At each iteration, gradient descent is using the entire data set. Okay, so the gradients are calculated on everything. But it does enable us to have stable and smooth conversions because it uses the exact gradient on the full loss. That's why you've got this kind of smooth convergence, okay? Now let's talk about the stochastic gradient descent equations. It's pretty much the same thing as gradient descent, except that the loss is going to be taking on different samples. Okay, so here we've got theta, the model parameters, weights and bias, pretty much the same. X, Y, one randomly selected training sample, loss for that single sample. So the loss is for that single sample, and then the stochastic noisy gradient estimate. And you'll see why it's noisy a little bit later. And then the eta is the learning rate. So here's the mini batch SGD. So we've got that equation, theta t plus 1 is equal to theta t minus eta, 1 over m summation, j equals 1 to m, and then we've got that loss gradient, okay? The gradient of the loss. Now this time we've got, if you remember from previous slides, we had n before, right? That large n. That small m signifies samples. So it's a mini batch size. It could be 32, 64, 128. I mean, it could be smaller than anything, smaller than that as well, right? 5 or 10. You choose n, but the samples are random, okay? Now, how would stochastic gradient descent work? This is like somewhat of a visual perspective. At each iteration, right, we take a random sample. So that would be a second iteration, third iteration, fourth iteration, and a fifth iteration, right? And we basically at each iteration compute the gradient on the sample of the data. What's important to keep in mind is that these samples may be noisy, right? So what I mean by noisy is that they might have higher variance and some might have low variance, okay? So SGD is computationally less expensive because gradient is computed on one sample at a time. And as I mentioned in the beginning, it's advantageous for large data sets. You can see that gradient descent has smoother convergence because stochastic gradient descent can use those noisy samples or those samples that just have high variability. The important thing is though is that it does converge, okay, even though this one looks it's a little bit out of scale, but it does converge, okay? So in order to make it a little bit the convergence to be a little bit smoother in GD, it's very common to decay the learning rate over time in SGD. So we've got eta naught times 1 over 1 plus lambda t, okay? And we basically decay it, make it decay. And this helps the noise updates settle down as you approach the minimum. And in practice, both GD often uses a fixed eta because the gradient is smooth and stable. So let's give a mountain analogy to stochastic gradient descent. Before I do that though, I want to make sure that you guys understand that zigzagging in SGD comes from the gradient variance and not the loss curvature, okay? So we saw like the loss functions being convex previously. It could be nonlinear as well, but that's not what we're focusing on. We're focusing on the gradient variance, right? The gradient variance of the sample, okay? So you could see from a mountain perspective that when we go down this hill, there's a lot of zigzagging where the gradient is changing, okay, um, constantly. And that's because of the different samples that each of those lines or those steps, those series of steps basically represent a high variance sample. And you can see that the last line that basically was projected on the mountain is a larger steps and it's steeper gradient. Here it's smaller steps and flat gradients, okay? Steeper gradients, it does lead to faster convergence, right? So in a previous slide, we saw that the learning rate, the larger the learning rate, it could basically hit the minimum faster, right? And you combine that with the gradient, it could hit it faster or it could overshoot. Flat regions are slower to converge, right? And this is a problem of vanishing gradients because they're near minima or saddle points, and the updates become tiny, right? So when the updates become tiny, training stalls, and this is common in deep network sigmoid tanh functions, and also poor initialization of the algorithm. And you could see that we basically hit some type of minimum, right? But it could stall, like I said, in flatter gradients, okay? And that's basically the gradient direction, okay, the steepness. So here's a stochastic gradient descent implementation. We've got this code initializing the parameters. And the only thing that we're doing different here is setting the batch size, okay? We shuffle the data, randomizing it. And then we loop through the data to collect a batch size of 4, and then make calculations in batch and compute the gradients. And you can see after 25 iterations or epochs, the parameters converge. So this is a visualization of comparing gradient descent with stochastic gradient descent. You could see that gradient descent, it's a lot smoother, right? And in the orange, the stochastic gradient descent, the convergence is pretty rocky. Finally, I'm going to leave off with talking about some different types of SGD. These are things that you could experiment with on your own just to see how it behaves, but I'm going to give a quick overview, okay? So we just saw this SGD, right? And the optimizer being the SGD, it uses raw mini batch gradients. It's basically a simple baseline and a noisy zigzagging path. There's also SGD plus momentum, and that accumulates past gradients. It reduces the oscillations, faster, smoother descent. There's AdaGrad, which is per parameter learning rates, sparse features, learning rate decays too fast. There's RMS prop, decay average of squared gradients. It solves AdaGrid's decay issue and it's stable for non-stationary loss. Then there's the atom, momentum, and adaptive step sizes, faster conversions, strong default choice. Atom W, decoupled weight decay, overregularization in atom, and then it solves for better generalization. Thanks for tuning in and happy holidays.